Hello everyone, this is Energy Crafts. Today I want to try to convert a Duracell Ultra three-way LED light bulb over to DC. What you see in front of you is a three-way which has the equivalent comparison to a conventional filament light bulbs of 40 watts, 75 watts, and 100 watts. As you switch your lamp switch in the three positions. But I want to change it to DC, so I'm not going to be using the three-way function, but I'm simply just going to use the LEDs in the assembly, and I'm going to forget about using the little circuit board that was originally there. But I will use the original LEDs and everything else. So for those that don't understand it in terms of 100 watts, the brightness would be 1600 lumens. So that's one of the reasons that I picked this LED light bulb to make the changeover, is because I looked on the market trying to find a 100 watt equivalent LED bulb, and I couldn't find any. I found 75 watt, I believe, and maybe I found an 80, but I couldn't find a 100 watt equivalent. So even at 100 watt equivalent, the actual power consumption on this LED bulb is 17 watts, I believe. You may be able to see it in the box information. So there's another reason I like this LED light bulb as well, is that I've tried converting LED light bulbs over from AC to DC on other types, and it was quite an ordeal to change the little PC board wiring, since it's so small and oftentimes it's hard to solder. So this one is should be far more easy to work with, because the only things we're going to have to change is not use the circuit board that's originally in the unit, and instead what we'll do is we'll use this little DC-DC boost converter. It's a constant current, constant voltage type. You can see the pots here. This one's the voltage, I believe, and this one is the current. I have not used this before, so this will be the first time I try it out too, so we'll both experience it. Some of the specs on this board is that the idle current is only 10 milliamps, so if you wanted to leave this running all the time, you could. I mean, it draws practically nothing by itself. Its efficiency is rated at 96%. It's got reverse polarity protection. The input, now this is really nice. The input voltage can range from 8.5 up to 48 volts. And the output can vary from 10 to 50 volts, and it's adjustable. But now, when I took this LED bulb and measured it when it was working from AC, what I registered was on using the three-position switch. Low was 43.3 volts, medium was 44.8 volts, and high was 46.1 volts. Going up to the little PC board module where the LEDs are soldered on. So we need to be able to cover somewhere around 43 to 46 volts according to the original voltages I was measuring. So this little DC converter, or boost converter, should be just fine. And it sounds like, since it'll go all the way down to 8.5 volts, that you could almost run your you could use a 9-volt battery for very limited time, but you probably could get away with it using even a 9-volt battery to run this monster. Obviously for not very long, but the point is how small a voltage you could get away with. It's That's pretty neat. But then you could always go all the way up to 48 volts or 50 volts or so. So this DC-DC converter will be very useful for alternative energy guys that are working with different kinds of voltages of batteries. And so we don't care about whether they're lithium. We don't care if they're NiCads. We won't care because this converter can work with any of them. So that's really all we're going to be changing is well, yeah, that's about all there is. And there is one more thing. Now, so what we'll have is we'll have the LED light bulb. We'll have the wires that are going to the LED light bulb, and then going into the DC-DC converter. I've got this from China. We have this 12-volt accessory plug with a switch, and it also has a fuse inside. So we will wire this in if we were going to use it for a 12-volt accessory. But for today, I'm just only wanting to hook up some sort of voltage, but 8.5 volts up to say 24 volts to the input of this for my power supply to drive it. So I won't be using this right now, but I'm just pointing out that for off-gridders, if you have a 12-volt battery with a cigarette lighter jack on it, obviously you could plug this into it, and then this would take the 12 volts and run it to the DC converter. All right, before we hook this up, let me show you what's inside this bulb. I have two bulbs, one that I'm actually going to be wiring up, and then this one that I'm just for a demo to show you what's inside of one, because I messed up my first one. And to save you from messing up yours, let me show you what I've done. So normally you have your light bulb, your LED light bulb, and this is the plastic globe, and then here's an aluminum heat sink, and then at the bottom there's a plastic round molding that is a little bit separate from this, but it's engaged into it. But I ended up breaking it off when I tried to get it off. And then this is the screw-in socket for your 120 volts normally. When you try to take this plastic globe off, it can be easy or it can be really difficult. Sometimes you can twist it and you can get it to break free in a spot, but usually you have to work a little bit, rotate around, and you use a screwdriver of some sort, and you prise at like a 45-degree angle, going carefully, not going too deep. Maybe you go 1/8 of an inch deep, and you leverage in two directions at once. You're leveraging against the globe, but you're also trying to force the globe out away from the heat sink, like trying to force it out. But you're also going sideways to do a twisting action. And you might have to go around this several times before you get it. But the reason you're going to be careful doing it this way is because this one I've already made it easy to take apart, so I'll show you here. When you pull it out just a little bit, you see there's only a tiny lip there. There's not much of a lip. So if you stick your screwdriver in there too deep, on some LED light bulbs, you go too much deep right there and you'll be breaking into the circuit board or damaging the LEDs themselves. In fact, on this one, when you pull your plastic globe off, be very careful to keep centered as you pull it off and try not to touch anything, because this heat sink that would have these LEDs on it, like this, you can see how close they are to the rim of the globe. So when you pull your globe off, it's very easy to scratch against these surface mount LEDs and rip them right off. So lesson learned, when you pull your globe off, pull it off very gently and slowly, and try not to scratch against the LEDs. And then the reason this is off like this is because this was one of my mistakes and messed up on the first one. Is normally you have the wiring, the two wires come up at the right here. I'll show you better. You have the two wires coming up here. One is marked plus and one's marked minus. The pink one is positive and the white one is negative. And it's just those two solder joints that we're concerned about for our modification also. But you won't be pulling the LED PC, whatever you want to call this little PC board. You won't be pulling it off like I did. I thought I could pull it off and make my own housing and start from scratch like that, but I destroyed this thing trying to get it off, and some of the LEDs quit working. So in your case, don't take this off like I did. Either you use it the way it is, or if it's got bad LEDs, maybe you can change them out. I tried changing them out. I'm not very lucky at it. I couldn't do it, so I give up on that. So I'll use this as scrap parts and maybe learn somehow someday how to take these off properly and to replace them on different LED bulbs. So just pretend this is on here for right now and it's still soldered up. But I'm going to take it off just for convenience. What you have under here is, this is a copper sheet under here, and then they have an insulated plastic, kind of like a silicone caulking of some sort on there, probably heat conductive, and then that's simply attached to this this piece of metal here, this hexagonal piece of metal, and that's the heat sink, and transfers the heat to these fins to the outside, and that's how it's supposed to keep cool. And then I was trying to get these two parts to come apart without breaking, but I found no way to do that. So when I finally prized this apart and broke it out, you see that there's two wires in the bottom here which would have been going to the 120, and those simply attach to this little circuit board right here. And let me pull the circuit board on out, since I already got this part removed. And there's not a whole lot to it, but unless it's real obvious, it's just not worth fixing. So this is junk in my case. So what we'll be using is all of this and this part, and we'll be rewiring to this. So I just wanted you to see how one is normally constructed. In all of its glory, before I do the modification to it. So really all it is LEDs, a heat sink, and a screw-in base, and of course the electronic module. But we're not going to be using this electronic module since we're using the DC converter. Okay, so now I'll put this to the side. Alright, so this is the real one that still works on AC, but as I said, I want to convert it to DC. So the only thing I've done preliminary that you didn't see off camera is that right here, in that little thick section right there, about 1/8 of an inch width there, I've drilled a small hole so that I could fish 2 wires that I'm going to be using to convert, that I'm going to be using to go to the DC converter output. And I've left them loose on purpose just so that you can see that all we've done is push them through the hole, and very carefully push them through the hole, because obviously drilling that hole left sharp edges, and I can't get to it to clean up those sharp edges. So what I'll do later is probably either put a blob of silicone in there, or I'll probably put a piece of heat shrink if I can fit it in there. But I'll secure it so that it can't wiggle around, and that way it won't chafe and short out. And we're gonna leave all of the LEDs on this one intact. We're not changing anything. But on the top, just like I showed on the other one, there is a red and a white wire. There's the original red and white wire right there in the solder. Before you start to solder these, take an X-Acto knife or something sharp and scrape the top of these solder joints, because most of the time they have some kind of a plastic covering to insulate them, and you'll never get solder to stick through it. I already tried. So scrape this, but be very careful when you're scraping that you don't start leveraging against any of these LEDs, because on my other one, I just barely touched some of those LEDs and they already started falling off. So try not to touch them. So on this setup right here, what I'm going to do is go ahead and now if you trust yourself, you could go ahead and solder these 2 wires onto the terminals just the way they are. But if you ever forget and you plug your LED light into 120 volts when you've already changed it over, then that would be very bad. It would probably damage the circuit board in there, and who knows what else it could damage. So in my case, I'm going to unsolder these 2 little wires and put my 2 wires there instead. But in terms of just functionality, if you don't ever plug it into 120 volts and you're only going to be using DC, then it would be even simpler just to solder the 2 extra wires onto what is already there and be done with it. But I don't trust myself or someone else to know that this is going to be only for DC. So in my case, I'm going to go ahead and unsolder these 2 little wires and just isolate them so that in the future, if I wanted to go back to 120 volts, we could. But I doubt we will. Okay, let me see if I can unsolder these. Kind of hard to do. And you don't want to get any heat close to these surface mount LEDs if you can help it. Got lucky on that one. Man, it's like a spring. Come on. There. Man, still not there. Finally. Don't want to put too much heat on that because that little flexible PC board, I found that the connections will rip right off if you get them too hot. and try to prise up on your wires. And then that would be very bad as well. Okay. Whew. Magic. All right. And don't forget which is plus and which is minus. That could be bad too. But we already know that this is plus. And you can fish these wires any way you want to get back down to the little drilled hole. The main thing is to not block the LEDs from being able to put out light, obviously. Have to freshen up my solder. Okay, I think that got that one. Whew. Now let's see if we can get the other one. You have to be careful it doesn't get caught on a sharp edge and rip it right out. Well, try that again. Well, third time's a charm. Looks like that was holding. So, well, one thing I should tell you is right here where I drilled that hole, to make it easy, what I did was first I drilled the hole right there in the center of that wall there, all the way through. But then I put the globe back on and then re-drilled the hole. And what that did was, what it did was put this little notch right here, and that's just enough for the wires to get through, and so that they can do what they need to do. So that made it convenient. Well, you know, basically the little notch is there to keep the wires from interfering with each other. So with that notch there, with that little notch there, should work. I had it working before. Okay, there it is. And when you're done with this, it'd be easy just to put a little bead of caulk. But I wouldn't put caulk everywhere, because what if you wanted to go back into it sometime? So I would just put caulk in a dab in a couple of places just to secure it, but still easy enough that you could use an X-Acto blade or whatever and cut it off in order to get back into it if you ever needed to. But if we trust what the LED manufacturers say, these things are rated like 30 or 40 years, so the little LEDs should just about never wear out. Should never go bad. And this on eBay I think is like $4 or $4.50, and this is like rated at 250 watts, so it's way overkill just to run my 17 watt LED light bulb. But this could be a main distribution if you're off grid, and you could run a bunch of LED lights off of this same DC-DC converter, since it has so much muscle. Okay, so now that we've got I've just got it held together loosely right now, but it's good enough, I think, that we could go ahead and test it and see if it will work. I'll be right back. Okay, I'm back. What I've done is I've simply wired the meter over to the output of the DC-DC converter. It's right here. This is the output side. And over on the input side, I simply have ran the black and the red wires over to a 12-volt power supply just from the bench. So what we need to do first is, since I haven't used this before, I have no idea where it's set at. So I'm going to turn on my bench power supply, and let's see. I believe this one is voltage, and this one on the outer edge is current. Let me see if that's true. Right now I don't have the LED bulb hooked up at all. I've only got the voltmeter hooked up, and I'm only looking at voltage. So going counterclockwise increases voltage, and going clockwise decreases voltage. So it's backward from American. So I calculated that I would need 49.6 volts, and I would need 300 milliamps. That's because the LED bulb is set up this way. It's 3 branches in parallel, and a total of 16 LEDs in series on each branch. And these LEDs require something like 3.1 volts, and they need somewhere between 100 and 150 milliamps. For me, I'm going to stay down at like 100 milliamps, because I just want them to last a really long time. So I'm going to go by what I measured on the good LED bulb when it was powered up with AC, and at the LED module it was 43 volts at low. So I'll adjust this to 43 volts. Wrong way. 43. 43.3 is what I had measured. Okay, I have no idea what the current setting is on the boost converter, but it doesn't matter because for right now, 43 volts without any resistors or current limiting device. It's all being controlled by the voltage drop on the LEDs, and 43 volts stays within the safety margin, so even without adjusting the current, it should not be a problem right now. So I think I'm just going to just bump it, not leave it on, but just a quick bump to vouch that it'll even blink. Let's see if it'll even blink. Whoa, it definitely blinked. How about that? So yeah, it looks like we've got something there. Okay, so the next thing I'll do, I think, is I will change the meter over to current, and I'll bump the LED and see what kind of current it's working at now. And then I'll adjust it down so that it's no more than 100 milliamps. That's just for my safety, but it can go up to 150 milliamps per string. So 3 times, I meant 3 times that. So in other words, I want to adjust this for 300 milliamps, because each string is 100 milliamps if I use the lowest rating. Because they say you can have 100 to 150 milliamps, so I'm picking 100 milliamps on the safe side. All right, I'll be back. We've set up the meter to measure current, and I haven't changed the voltage. It's still at the 43.3 volts, and now we're reading, looks like 91 milliamps. I don't know if you can see that. It was 91 milliamps. Looks like it's going down. But what I want to do now is figure out which way the current goes down. I know you can't see it. I'm adjusting the current on the little circuit board. So the milliamps is 94.8, and I've been adjusting the pot either direction, not seeing any real change. So I think I'm going to put a 12-volt load on here and determine which way the current goes in the pot, because right now I can't tell. But even without adjusting the current pot, the LED bulb can only give what the voltage drop allows it to. So the current is around 100 milliamps, and that's on the low end of typical use for these LEDs. So it should be fine just the way it is. And if I wanted to make the light bulb brighter, all I have to do is crank up the voltage. 43.3 volts was the low setting, medium was 44.8, and high was 46.1. So, so I might do that too, but this proves that it works, and this is probably the simplest way to get a high lumen output LED that's pretty much already made, and all you do is change the little PC board and trade for a DC-DC converter, and then you're back up to running. Very flexible, because if I wanted to go back to AC, you saw the two soldering connections. All I had to do is replace those connections, and we'd be back to normal AC use. For me, I'm going to take this light bulb and I will solder it, not solder it, I will install it into a typical lamp socket, and the way it is now, whether if somebody happens to plug in the 120 volt plug, it won't do anything since I've desoldered the wires, although the little circuit board would still be alive. So, but it would draw practically nothing since there's no load on it with the LED module not connected to that part. So I think this is a good way to go. Now, if you want to go deeper and break this plastic piece off of the down here at the bottom, if you wanted to break this dividing section right here away, then you could remove the circuit board altogether, like I did on the one that you saw earlier. But I think we're okay the way we are. Well, I hope this was enjoyable, and thank you very much for watching. Have a good one. And I was looking at trying to adjust this current control on the boost converter, and I couldn't get it to change. Now I know why. With the LED bulb that we were using, it only draws somewhere around 100 milliamps, as you already saw. And I was looking at the data sheet again, and here's why we couldn't get an adjustment. It says the output is 10 to 50 volts adjustable and 0.2 to 8 amps. So 0.2 amps is as low as you can adjust it down to. So you cannot adjust it less than 200 milliamps. And that would explain why I adjusted the current pot on this boost converter and couldn't get anywhere. I changed out the LED light bulb, and I hooked up a small electric fan motor, and I was able to adjust the current just fine. So until you get below the 200 milliamps, and then you couldn't control it. So here's a situation where, even though we're using a boost converter with constant current control, that's constant current at 200 milliamps in this case is all that it controls to. So the fact that the bulb only uses 100 milliamps, that means if there was something wrong with the LED bulb circuit, say some LEDs started shorting out and it started drawing more current, it would draw all the way up to 200 milliamps at the worst case. So even though it's constant current, it's not constant current for the actual 100 milliamps that I'm wanting to work at. So, but it's fine because we're using 3.1 volts as the voltage difference per LED, and times all the LEDs, that means that 43 to 46 volts is okay in that range to make sure that none of the LEDs ever see more than 3.1 volts. As long as they don't see more than 3.1 volts, then the current won't go over 100 milliamps no matter what. So that's the other way to regulate is to make sure that your voltage drops per LED don't exceed the recommended range. And I think it's 3.1 to 3.3 or something. But again, I use 3.1 at the low end to work with. So that means that these bulbs won't even get hot like they would have gotten hot before using the little circuit board that's built inside of the LED bulb. Now that we're not even using that and we're using an external board, there won't even be a heat issue. So we could actually even scrap the heatsink if you wanted to, but since it's part of the shape and to hold the globe on, might as well just keep it. All right, well, now there is one more thing I forgot to say. This is starting to get too long, I know. I wanted to point out that I only hooked this up quickly just so that we could get something and demonstrate this thing working. But what I'm going to do now is I'm going to take some 5-minute epoxy, and I'm going to put a drop along this edge here to secure these wires so they don't move around. And up here on the top, I'm going to put a drop of 5-minute epoxy, just a drop, to secure those wires so that they don't put any mechanical strain on those solder joints, because those solder joints are very weak to the little PC board. And other than that, we are done. And of course, when you caulk your, after you put the caulk around the globe and put it back on, don't forget to put the little drop of caulk inside here where that hole is so that you don't have a shorting or a chafing situation with the wires. Or put heat shrink. And other than that, I think we're done. Right here I showed the fact that we're just using alligator clips, but in the real world, what I would do is I would take these two output wires and I would twist them around each other, or you could put it in a drill and spin it and hold it carefully, and I would put a little connector on the end. Just put a little connector here that would then connect to whatever extension or wiring, because I don't know how far this is going to be from your actual battery bank or whatever, but just use little plug-in connectors to make cables and go wherever it is that you want to go to. But for just demonstration, I was just using alligator clips. That's not real-world usage. That's just for testing purposes. So you would want to make this nice and tidy with nice secure connections, and guess that's about it. Should last for like 30 or 40 years if everything is true like they say in the specifications. Okay, now we're done, and I hope this wasn't too long for you, and hope this was useful to you in your own off-grid projects. Thanks. Okay, so now let's set it up in a desk lamp and see how it looks. So, so far I've got a lamp fixture here, and here's our LED bulb, and there's the wires still connected just to alligator clips. And as you see, the regular 120 volt plug is not going to be used. It's simply just there. And the bulb is screwed in the socket just like normal, but our power will be coming from the DC to DC converter here, and instead of a battery for right now, I'm just using my portable lab power supply. And So it's almost ready to go. All I have to do is put the shade on. Put the lamp shade on here. And just a moment. Okay. And then all we got to do is turn on the power supply. So we'll do that. And of course, we have light. And I don't think this is a full 100 watts worth of light, equivalent worth of light. But on the other hand, my lab power supply only is good to 1 amp, and I'm using 12 volts. So 12 watts is all I can get out of my power supply. So that would have explained why it's not all the way to full brightness. And let's look at the voltage at the LED light and the current. And looks like the voltage is 46.1 and the current is 0.25 amps. So definitely under the 0.3 amps, which would be our limit. Okay, well, that is, I would consider this a success. And hopefully you enjoyed this and got something out of it. Last note I'll mention is the original voltages I mentioned that I measured on another light for the low, medium, and high voltage. Sorry, low, medium, and high switch positions. I'm not sure those are correct because this was an LED bulb that was thrown away, so there must have been something a customer wasn't happy with, but it may be those voltages are off a little bit, and that's why the customer didn't like it, because it wasn't given quite the same brightness as maybe other bulbs. So if anybody knows what the true voltages should be at the little regulator board in the original LED lamp, I would love to have that to compare with this. But I would say this is a success, and definitely very useful, especially for off-gridders that want to use DC power to power everything and not have to use inverters. Alright, have a good one, and thanks for watching.